We can think of a harmonic wave as the sum of many small parts, each part being a simple harmonic oscillator. Each oscillator is slightly in advance of the one following it, and slightly behind the one preceding it. In other words, they are slightly out of phase with their neighbors. The wave is merely a continuum of these oscillators. The amplitude is the maximum distance that the motion reaches from its equilibrium position. The amplitude of the motion does not affect the period, wavelength, or speed of the wave. The wavelength describes the distance between any two identical spots on the wave, crest to crest, for example, or trough to trough. The frequency is the number of cycles that occur in a unit of time. A high frequency implies a short period. The period is the time it takes a wave or oscillator to complete one cycle. In simple harmonic motion, this occurs when the point occupies its original position and has the same velocity and acceleration. A small period implies that there are many cycles in a unit of time. The speed of a wave is the distance the wave travels divided by the time it requires to travel that distance. There is a fundamental relationship between a wave's speed, its frequency, and its wavelength. Wave speed equals the wavelength times the frequency. There is a fundamental relationship between a periodic wave's speed, its frequency, and its wavelength. The wave's speed is determined exclusively by the media in which it moves. Selecting the frequency at which we drive the wave then fixes the wavelength. Consider a moving wave. The time it takes for the wave to return to the same phase is one period. This is the same time it takes the wave to travel one wavelength. The speed of the wave is therefore the wavelength divided by the period. Because period and frequency are inversely related, the speed is also the wavelength times the frequency. In 1995, a magnitude 6.9 earthquake devastated the city of Kobe, Japan. An earthquake's power rolls through the ground as a torrent of vibration. The cart is on wheels and, by Newton's first law, remains at rest as the building moves around it. The motion is fairly simple. It approximates a repeating oscillation called simple harmonic motion. An earthquake's destructive energy is transported in waves. In this module, we learn about simple harmonic motion and waves. The period of a simple harmonic oscillator is independent of its amplitude. These two oscillators have the same mass and spring constant. Despite the large difference in their amplitudes, both motions remain in phase at all times. In our spring and mass system, we can trace the path of the mass over time. We create a plot of simple harmonic motion. All simple harmonic motion can be represented by a curve of this general shape, a sine or cosine wave. A pendulum exhibits simple harmonic motion provided that the angle of swing is not too large. The motion of a transverse wave is perpendicular to the direction of energy flow. The energy of a longitudinal or compression wave travels in the same direction as the motion of the wave. A water wave is a combination of transverse and longitudinal waves. The longitudinal compression moves in the direction of the energy flow, and the transverse motion is perpendicular to the energy flow. This combination results in a single point in the wave tracing a circular path. A torsional wave is similar to a transverse wave, except in this case, the motion of the wave moves around a central axis. The axis is oriented in the same direction as the wave's energy flow.